Linear programming problem. Linear programming problem. Let Xij be the number of units to the transported from the sources I to the destination j. So where I equal to 1 to m and j equal to 1 to n. That means here xij equal to air coolers, uh, number of air coolers to be transported from Hyderabad and Mumbai to Bangalore, Chennai, Delhi, and Ernakulam, respectively. A linear programming model of this problem is given as follows. The objective function maximize z equal to 110 x11 plus 90 plus 75 plus 55 plus 65 plus 50 80 plus 45 So the constants are x11 plus x12 plus x13 plus x14 equal to 300. So x21 plus x22, x23 plus x34 equal to 100. 100. x11 plus x21 less than or equal to 85. x12 plus x22 less than or equal to 150. x13 plus x23 less than or equal to 150. x14 x14 plus x24 less than or equal to 50. So here xij greater than or equal to 0, where I equal to 1 to and j equal to 1 to 4. In the above LPP, number of uh, number of uh, variables number of variables equal to m cross n, that equal to 2 cross 4. So number of constants m plus n equal to 2 plus 4 6. So example, convert the following transportation table into balanced problem. So destinations, to from. So origin source, table. A solution for the given problem. Number of destinations m equal to 3. Number of sources is 3. Here destinations and origin or source. Supply demand, nothing but. Here 2 from D1, D2, D3. Supply AI. So S1 equal to 30, 50, 30, 50, 15, 300. S2 equal to 35, 70, uh, 70, 20, 290. Hence, it is unbalanced here. Sigma AI equal to sigma I equal to 1 to n, AI equal to A1 plus A2 plus A3, that is 300, 200, 500, 1000, 1000 here. J equal to 1 to n, Bj that equal to B1, B2, B3, that equal to 300 plus 200 plus 900. So here A sigma I equal to 1 to n, AI is not equal to j equal to 1 to 1 to m. 1 to m. So this is given problem is unbalanced. So we have to make it balanced. How to make it balanced? I have to choose. No. Here, here it is an unbalanced transportation problem. Under this situation, an additional an additional source or destination is to be included in the table. If ji equal to 1 to n, ai is greater than j equal to 1 to m. Number of sources is n. Ai bj is supply, demand bj. Number of destinations 3. Number of sources 3. Destination 3. Sources also 3. So here it is unbalanced transportation problem. Under the situation, an additional source or destination is to be the include in the table. So j equal to 1 to m ai greater than j equal to 1 to m bj. Eh? That, yes, then include a dummy destination to be observed the excess supply. uh, the demand of the dummy destination is equal to j equal to 1 to n aj minus j equal to 1 to n bj. The cost coefficients in the dummy destination are assumed as zeros if j equal to m aj less than j equal to 1 to n bj. Then include a dummy source to supply the excess demand. Supply of the dummy source is equal to. So here supply of dummy source is equal to j equal to 1 to n bj minus j equal to 1 to n aj. The cost coefficient in the dummy source are assumed to as zero. So the given table is modified modified by including dummy destination. So sigma I equal to 1 to 3, aj equal to 100 is greater than j equal to 1 to n bj, bj that equal to 900. The cost coefficient of the dummy destination d4 at which is 100 units are required. 100 units are required. This is shown in the table, which is which is now a balanced transportation table. Trans- Transportation table. Destinations. uh, Sources. So D1, D2, D3, etc. S1, S2, S3. Demand Bj. So here D4. D4 is dummy. DM dummy 00 with a zero cost we need to take. So next. So existence of solutions in transportation problem. Existence of existence of existence of solutions in transportation problem. The general transportation uh, problem always has a solution. Uh, so 10 point. A necessary and sufficient condition for the existence of a feasible feasible solution to the general transportation problem is that so sigma I equal to 1 to m ai equal to sigma j equal to 1 to n bj equal to lambda. So total supply equal to total demand. To necessary condition. What is the necessary condition? Let there exists a there exists a feasible solution xij to the transportation problem, then we have j equal to 1 to m. Sigma. A necessary condition. What is that? What is the necessary condition? Huh? Let there exist a feasible solution xij to the transportation problem. Then we have j equal to 1 to m xj, I equal to 1 to m, j equal to 1 to m xij, that equal to b, bj I equal to 1 to n. Then I equal to 1 to m, j equal to 1 to m xij, that equal to I to 1 to m ai. Yeah? And j equal to 1 to n, I equal to 1 to m xij equal to j equal to 1 to n bj, that equal to j equal to 1 to n aij, sigma I equal to 1 to n, j equal to 1 to m xij, uh, j equal to 1 to n, I equal to 1 to n xij. So here what is there here? Uh, j equal to 1 to m aij, that equal to j equal to 1 to n bj equal to lambda, say means let. So sufficient condition. Choose that there exists a feasible, yeah, xij given xij equal to ai bj lambda for all I and j. Clearly xij greater than or equal to 0 since ai greater than 0, bj greater than 0 for all I and j. J equal to 1 to n xij, that equal to j equal to 1 to n ai bi by lambda, ai bi by lambda a1 lambda, so j equal to 1 to n bj, ai. So for all I equal to 1 to m, I equal to 1 to m xij, that equal to I equal to 1 to m ai bi, bj lambda. So here bj by lambda, that equal to j I equal to 1 to m ai bj for all j 1 to n, the xij satisfies all the constraints of the transportation problem, and hence it is a feasible solution. So corollary, corollary what is there here? Uh, existence of an optimal solution. Uh, So there always exists an optimal solution of transportation problem. Proof. Let let us suppose that the transportation problem uh, is balanced. The relation sigma I equal to 1 to n ai is equal to j equal to 1 to m bj, holds so that a feasible solution xij exists. It follows from the constants of this problem that each xij is bounded 0 less than or xj less than or equal to minimum of ai bj. The basic feasible solution. What are the basic feasible solution? Here the number of basic variables in a transportation problem with the origin and n destinations is at most m plus n minus 1. Proof. Consider the following m plus n uh, constraints of a balanced transportation problem. J equal to 1 to n, xij equal to ai, I equal to 1 to m. Uh, j equal to 1 to m, xij equal to bi, j equal to 1 to n. Taking summation on both sides yields. So, I equal to 1 to m, j equal to 1 to n, xij that equal to j equal to 1 to uh, 1 to m. Ai equal to j equal to 1 to n bj. So, uh, summing the first n minus constants of we get uh, j equal to 1 to n minus 1. I equal to 1 to m xij equal to j equal to 1 to n minus 1 bj. Bj. So, subtracting 4.9 from 4.8 we get here sigma I equal to 1 to m, j equal to 1 to n, xij minus j equal to 1 to n minus 1, I equal to 1 to m, xij that equal to j equal to 1 to n, bj that equal to j equal to 1 to n minus 1 bj, r I equal to 1 to m, j equal to 1 to n xij minus I equal to n minus 1, xij bn, r I equal to 1 to m, xm equal to bn. Which is precisely the nth constant. Uh, uh, so, thus, one of the m plus n constants is also and may be removed from the set of constants. Hence, a basis constants of at most m plus n minus 1 uh, variables. M plus 1 variables. Next. So loops in transportation tables. What are the loops in transportation? In a transportation table, an ordered set of four or more cells, cells is set to form a loop. uh, uh, if any two adjacent cells in the ordered set lie in the same row or column. So second, so not more than that two adjacent cells in the ordered set lie in the same row or column. Uh, the first and the last cells in the ordered set lie in the same row or column. So the ordered set must involve at least two rows of the table. Uh, The loops are closed that their endpoints are coincided. Uh, 4.5, three different loops in the table 4.5. 4.5, 4.5 BC, ABC. So here, first table, here loop. Uh, Next, corollary. A feasible solution of a transportation is called basic if and only if the corresponding cells in the transportation table do not form loop. So remarks, every loop has an even number of cells. So the allocation are set to be in independent position if it is not possible to increase or decrease any independent uh, individual allocations without changing the position of these allocation, that is closed loop cannot be formed through these allocations. What is the a loop may cross itself, and even crossing point may be non-basic cell. a loop can skip over some basic cell or non-basic cell in row and column. However, the success lines must be perpendicular. The always exists a unique loop starting from a given loop basic cell. So each row and column is the transportation table should have only one plant and minus one plus and minus signs. So summary. So what we discussed today. So transportation and assignment problem. We discussed an introduction uh, and mathematical formation of transporting mathematical form of transportation problem. Uh, Formation of the transportation problem and types of transportation problems. What are the types of transportation problem? Balanced transportation problem, that is sigma I equal to 1 to n, ai is equal to sigma j equal to 1 to m, supply equal to demand, or requirement equal to availability. uh, Availability, uh, requirement, demand, supply. So next, what is their unbalanced transportation problem? If the sum of the supplies of all the sources is not equal to the sum of the demand of all the destinations, then the problem is termed as an unbalanced transportation. Uh, it is represented as sigma ji equal to 1 to n, ai is not equal to j equal to 1 to m vj. So transportation table next, formation of LPP means linear programming problem, a transportation problem, right? So example, convert the transportation problem. Huh? So solution. Here it is not unbalanced transportation problem. We have to convert it into balanced uh, balanced transportation problem by adding dummy column. So D400 dummy column means with zero cost. Huh? So okay, I'm leaving. Okay, thank you very much. I'm leaving. Yes, thank you.